All right, welcome back, my friends. This is William M. Briggs for episode 48 of Uncertainty and Probability Theory, the Logic of Science. Today, well, we essentially start anew. We start from the beginning. This is the point at which most courses sort of start, in a way. We're going to discuss what is a model. Almost all the time when you well, I can't even think of any exceptions, so I'll just go ahead and say all the time. You take any kind of statistics course, they immediately start with models. They immediately start you on models as if everybody knows what a model is. It's absolutely unambiguous, as if models can discover cause, all kinds of assumptions. We went through 47 plus two others. I guess there were 49. Almost an entire year we've been at this, looking at everything that can go wrong. I've emphasized all the points at which we could be over certain, about which we don't understand enough, about which we try to make assumptions and things can go absolutely wrong, about what's the weaknesses of falsification, about the full richness of causality. We devoted weeks and weeks to causality. We talked about induction. We talked about how we deduced any of these models, probabilities in the first place, all these kind of things, proving that probability is just giving us our uncertainty in proposition based on some evidence. So that's what we have here. So what is a model? That's a model. All models look like this, and no exceptions. Now, there's going to be all kind of thinking about exceptions, and I'm going to try to prove to you today that there is no exceptions. We want to know the in science, we constrict Y to be usually about some observable, but we could have it any proposition, a particular theory. A theory can have as a statement, is a set of propositions, which we'll come to here in a second. We've discussed this before, but I really want to hammer it home today because, and I'm going to show you a little bit of this today here too. We're going to look at some math, our first mathematical model. Besides, I think we did, I can't even remember. We did some very simple Bayes theorem kind of calculations and so forth. And so we're going to continue along that line. But you're going to become enamored of the model. I've warned you not to. I've warned you that you must not become so infatuated with the math that you begin to think the math is realer than reality. This is the deadly sin of reification or reification. This is the fundamental cardinal sin that most scientists make. And I've told you about this, I've warned you about it, I've showed you all kind of examples about it, and you're going to do the same thing. I'm telling you right now, you're going to do the same thing. You won't be able to help yourself because the math is so rich and so beautiful, and it's hard work. And anything that you put a lot of hard work into to sort of prove to yourself, aha, look at this rich structure here, you're bound to take it more seriously than it should be taken, especially when you want to apply it to reality. So let's begin on this simple thing. So any logical argument, which is what this is a logical argument, given or accepting or believing or for the argument's sake, some set of evidence E or some propositions E, whether or not they're true in the world or not, doesn't make any difference. We want to calculate the probability of this proposition Y. There's all kind of models that we use all the time in real life. People use models all the time. What time is I don't know. What time is my wife going to get home from work? I don't know. She gets home between 5 and 6, usually. Well, if you had to pick a time, what's the probability she'll get home before 5:30? Well, you have, I don't know what the number is. I don't know. It's pretty good. We have all kind of things like this. Or you see some guys, you saw some deer running around in the woods over there, and then somebody asks you, how many deer did you see? Well, I don't know. I saw a couple. What's the probability that there were actually 4 deer over there? Somebody might ask you something. Why they would, I don't know. But you don't know exactly. You haven't got any kind of firm model on this. You're just guessing, there might have been 4. Maybe not. I only saw a couple, but they're hard to see in the woods. Models like this happen absolutely every waking minute of our life. We all are often judging these models. We're not thinking that they're models, but that's exactly what they are. Anytime we make any kind of rational argument from some premises to some conclusion, and we're either certain or uncertain of the conclusion, we have made a model. That is a model. And most of these models we use in real life, absent any kind of mathematics or expert guidance, especially without expert guidance, are real good models. Is it going to rain today? How much traffic is there going to be? How much should I spend? I mean, not spending, that's a decision. But, anything you're going to do that involves absolutely any certain uncertainty, whatever. Should I get off, maneuver into the right-hand lane now or wait? What's the probability it'll be more crowded? Just endless examples like this. All of these are models. They're absolutely models. But they're not formal models. What makes a model formal? There's nothing really that makes a model formal. The distinction is wholly arbitrary, but with some uses. What makes a model formal is when experts bless the model, or they turn it into mathematics, when it becomes the consensus in some field or something like this. And there's all sorts of good reasons to do this. I'm not saying we shouldn't use mathematical models. I use them all the time to make a living. But it doesn't mean that because we've come up with mathematics, that mathematics applies to the real world. There's this guy, maybe I misunderstand him, but there's a guy named Max Tegmark, if I'm pronouncing his name correctly. He's got some hypothesis that all mathematical objects exist or will exist. Well, that's just silly. Maybe I misunderstand him, but that particular statement is absolutely silly. I mean, because I can write down any kind of list of equations here. We can just go to town writing equations. There's an infinite number of equations. And it doesn't mean just because I'm able to write down this equation that it applies to the world in the way I say it to. Mathematical equations are just symbols. And they're symbols that we apply meaning to. Okay? And that's that meaning that gives us the model and so forth. That's one of our assumptions, is that this math, as we'll see, I'll give you a real simple example today, that this math means what we say it means. The math itself is inert, lifeless. There's nothing to it. It's us who bring the interpretation to the mathematics. The mathematics doesn't have it itself. So to say that mathematical objects exist, or that just because we wrote down an equation and we said y equals this real thing in the world, that it really does, that's not the case. And later in this course, we'll learn how to make those judgments. We'll look, I said this was a good model. How do I tell? How do I tell? So we're going to learn how to do all that. Okay, so now there are some people who differentiate between a theory and a model. They'll say that we use the theory to generate models. And that's true only in a bureaucratic sense. It's true that if you're trying to do bookkeeping and the like, and you've got some theory of gravitation, general relativity, and you're trying to calculate GPS coordinates or something like this, that's my general theory. But now you have to come down into real life and make a model about how this actual satellite's really going to work and all this kind of a thing. Well, it's all the same thing. It's, in the end, it's a list of premises that you assume are true. That's it. Everything to me, it's an eccentricity on my part, I agree. I don't use the terms as other people do, and I wish people would use my term, because these are just logical arguments. That's all they are. And if you have this list of premises here, so E is going to include the grammar, the definitions, the apprehension of the terms, and whatever data we have in all this. All of that stuff is part of E. Normally, I've told you many times, when we're writing out a mathematical model, all of that stuff is in E, but we don't actually write it out. It's there, and we should remember it's there, and most of the time when we're working for ourselves, we'll remember what went into E, but other people can't see it. Other people can't see it. And because of the deadly sin of reification, they believe because we haven't written that stuff down in E, it doesn't really exist. But it's always there. And so I'll come to what I mean by that when I talk about all these mathematical models and so forth. So really, in most real-life situations, E is our evidence that we have here. And I've gone over equations like this before. E is itself it could be even unarticulated propositions that we have, only vague notions of, and that's absolutely fine. for most of the models we use in working life. But as we become more formal and we become more mathematized, or if that's even a word, we make mathematics out of all this kind of stuff, we tend to turn these things into math, and that math just becomes even realer than reality, when oftentimes simpler models are better. Anyway, this evidence is, this is proposition 1 married to proposition 2 married to this proposition here, which are these other propositions. It's either it's this and this, or it's this and that, in union with a whole bunch of other propositions way out here. Some enormous list. Because, again, we have the grammar, definitions, the apprehension of these terms, and all that stuff is in there. It all is in there. And one of these might be PJ, I'll call it. It's data that we have. We have observation 1, which may itself be a single dimensional thing, or maybe multi-dimensional, doesn't matter. Union with observation 2, 3, up to n. All of that stuff makes a model. Absolutely all of that. This is E. All of this stuff is E. Now, if we change E to F, which is exactly E, which we could do, I'll use an abusive notation here, minus P17. Which, or I could do it like this, or I could say F is another model that I'm going to have E, where we're going to take out this one right here. We're going to add ON plus 1 plus ON plus 1. These are not E. These models, where I make any change here, and the change has to be relevant, and I'm going to save relevancy and all that kind of stuff for another day, but I'll let you think about it now in a very loose way. If it makes a change in the probability of Y, given everything else I have in the model, then it's relevant. But if I make any change to E, I have a new model. That's not what people tend to say, because they want to stick to their theories, and they have all sorts of models that they manipulate. And again, that may have all kind of bureaucratic uses to keep things separate and trackable and so forth. But it's a new model. Any change, anytime you add a piece of data to your model, it's a new model. Anytime you take a piece of data away, it's a new model. Any change whatsoever that's relevant to your proposition of interest, it's a new model. All right? Any change. That's the way we're going to handle this. I know that that's not how people do it, but that's what it is in logic. That's the full logic of the situation. So we need to absolutely keep this in mind. And someone was arguing with me on Twitter, and they said, well, you can't have a theory. What's the probability quantum mechanics is true? So why for them was quantum mechanics? They thought they had caught probability in some kind of contradiction. Well, I first said, well, okay, what's the probability quantum mechanics is true? All right, well, that depends on the evidence you're assuming, which is all this big stuff. And it more importantly depends on what's your definition of quantum mechanics. That's part of this evidence. What do you exactly mean by quantum mechanics? And I said, well, it's going to look something like this. Whatever that, your particular statement of quantum mechanics is, it's going to be something like this. He said, well, okay, maybe that's right. But then you should be able to get the probability of not QM. I said, that's exactly right. You certainly can. If this is your evidence right here for quantum mechanics, the probability it's not E. It's not this evidence, which means not that every single thing in this evidence stream, if you like, this complicated proposition is false. Well, give it E anyway. See, now I don't want to contradict myself here. If probability of Y being, well, I'll use quantum mechanics as our example here. The probability that quantum mechanics is true, given E, plus the probability that quantum mechanics is false, I'll give it a complement there, well, that's going to equal 1. Because either one or the other, except on this evidence, where this evidence stays the same, is that's just basic probability we did back, I don't even episode 2 or 3 or something like this, or probably 4 or 5, because we had to first prove we could turn probability into math. Well, that's absolutely true. The probability of quantum mechanics is true given this evidence, and the probability it's false given the same evidence has to equal 1. But if you want to say they thought that we had an exception about this evidence here. When you say not E and you don't believe this evidence, that doesn't mean every single thing in the evidence is wrong. When you say a model's wrong, what's the model that you have or the propositions you're entertaining to believe whether quantum mechanics is true? It means at least one of these things is different or false. Instead of P2, it'll be P2 is false, and every single thing else could be right. Or it could be absolutely everything in here is right except for this one here. We made an error in a measurement or something like this. So we're going to talk about all that and how to measure all that and how to dive deep into these kind of things. But it's just standard logic. We haven't done anything new. That's what the whole point of the first part of this class was, is to show you that probability is just the completion of logic. And so you treat these statements as you would treat any logical statement. There's no difference. There's no magic happening or anything like this. Okay, so here's an example. I guess you could see it here. You don't need me to erase anything. So people will say, well, I have this, given whatever evidence I have, again, the probability that Y will be true, and Y is going to be, in this case, singular, something that can happen or not, some dichotomous observation in the world, yes or no, true or false, on or off, something like this, above a certain temperature or equal to it or below, whatever you like. And they'll say, well, the probability that, they'll just assert something like this, the probability that Y is true, given this evidence E, is pi. That's a common notation to use, pi. And then they'll say, well, that's too easy. What I really want is I want to have a function of pi. So I'm going to take the odds. Odds, remember, is just probability divided by 1 minus the probability. And I'm going to take a function of those odds, and I'm going to say it's equal to this, which is just some parameter, a parameter, beta 0 plus beta 1 times x, where x may be some observable in the world, some measure that I take about something like the incoming class size, or somebody's income, or their weight, or the temperature yesterday, or any number of things that I might want to have about the world. And I put them all into this model here. I say the log odds of this parameter pi here is equal to this linear equation. This is almost always ad hoc. 99.999% of the time, this kind of maneuver is absolutely ad hoc, meaning seat of the pants. They made it up. It seems convenient. And because everybody else does these ad hoc models, I'm going to do this kind of an ad hoc model. Well, we can back out the probability. We can back out pi from this. Just back solve this, and here's what pi equals. It's this exponential of this divided by 1 plus that exponential. That's what pi equals. So the probability of Y now equals the exponential of beta 0 plus beta 1 x1 plus beta p xp, all divided by 1 plus this same exponential. Okay, fine. Now, we know what x is 1 and x, these are measures we make in the world, x1 here and all the way up to x. We can make measurements in the world, but what do these betas equal? Well, we made them up. We made them up. This thing is just ad hoc to begin with. They don't exist. But, however, that doesn't affect us when we're doing probability. We talked about probabilities of unicorns and Bigfoot and happy feminists, and all that kind of, non-existent creatures. But we could still do probability on them. And we could do probability on these non-existent parameters. The real thing that happens, again, is the deadly sin of reification. This starts to get slick. It's fun when you realize you can do this kind of oh, you mean I could take this parameter of the probability of Y happening and relate it linearly by some function to these measures I take in the world? That's kind of nifty. That's kind of nifty. And I could calculate all these things. But then people start talking to themselves and they reify it. They start talking about the true values of these parameters. What's the true value of beta 1? Beta 1 is the effect of x on y. No, it isn't. It's just a parameter that kind of helps you relate the correlation of x, x1, and y. It's just a correlation. After all, we have no causality in this model. If we had causality, because we're always after models in the end. I'll tell you here we go. Here's what we really want. For every model, we want the probability of y being, given the full explanation or cause slash cause. Remember how we did that over thing? That's either going to be either in the set 0 or 1, depending on what y is, related to its full explanation or full cause. That's what our goal is in everything. We want to be able to deduce things. That's all this is. This is a complete deduction. All probabilities are deduction, but we want to come to absolute certainty, either 0 or 1, when we know the full cause of absolutely anything. This is just a correlation model. No matter how sophisticated it looks, this is called, by the way, I should have told you, this is called a logistic regression. And this is the logistic function right here. That's that part of it. The regression part I'll explain later, but that doesn't make any difference to us today. This is a logistic regression model, and it's ubiquitous. Regression models are ubiquitous. They're absolutely everywhere, used all the time in all kind of fields. They're always correlational. Every single one of them is correlational, but they're always claimed to be causal. And people think, well, if I take one of these out and put one of these in and look at it in this way, now I got a causal model. You don't have a causal model. If you knew the cause, you'd put it up here anyway and you'd be done. It doesn't work that way. You can't get caught. You can't back causality out of these things so easily. You can learn cause, absolutely learn cause, and we build up evidence to learn cause, but those are always inductive leaps, as I hope to prove to you. I gave you enough evidence about cause, of how difficult it is to discern cause over the last several weeks. Anyway, we have all these things here. So when people start talking about true values of these, oh my God, what's the true values? We need an estimate and a confidence interval around these things to tell us what the true value is. Well, you just pulled this model out of the nether regions. There's no true value to something that you made up. How many toes does Bigfoot have? Well, what's the true value of the number of toes that Bigfoot has? Well, we can make guesses. We can come up with all kinds of things. And in the end, we're just making it up. All right? These parameters don't exist. And so this model can never be more than correlational. And correlational models can be very useful. All right? They can be absolutely useful. There's no question about that. I don't say that we shouldn't use these models, but we should always keep their limitations in mind. We should always understand that we can't make fully causal claims when we're making these models. We can talk about correlations, which means we're still searching for full causes and so forth. Anyway, but because of the allure of this, there's it stops here. People never come back to this. They never give you the probability of y. They instead talk about these parameters. All concentration, all focus becomes on these parameters. Frequentists will give you estimates. They'll put little hats over them like this. They'll call them hats. They'll call that beta hat. These little carrots over the betas. And they'll come up with an estimate, and they'll come up with a plus or minus interval that doesn't mean anything that they think it means. Every frequentist theoretician is secretly a Bayesian. Even if they are an occult Bayesian, even if they don't know it themselves, and I'm going to prove that to you too. Or a Bayesian will do the same thing. They'll put it in here and they'll call their interval a credible interval, which gives you some uncertainty in this parameter. What's the true value of this parameter? They're always saying, there is no true value of this parameter. We don't care about these parameters. Really what we want to do is there's something, I'm going to go over all this. I'm just giving you the highlights today. I'm not proving anything here today except that I didn't even prove this. This we already knew. That I'm just giving you my eccentric notation here. But we already knew all models were like this. I'm just kind of highlighting it here today. Really what we want to do is we want to integrate out the uncertainty we have in these parameters that don't exist anyway. And we want the probability of y, given the evidence that we have. That's what we want. That's what we started out asking about. And we said the probability of y is related to this parameter here. Okay, that's fine. We can give it a name. There's no harm in this so far. But we'll say, now I want to have a function of this thing here and say what this probability parameter itself looks like if I model it like this. No harm in doing that. But in the end, I don't care about that. What I really want in the end here, and the evidence here, I could expand this. This probability of y given the evidence is going to turn out to be probability of y given. Part of that evidence is x1 and x2 and xp, whatever that's going to be, and the rest of e. Rest of e. Whatever else we put in there. That's what I want. I started out wanting to know what this was and not wanting to know what this stuff over here was, but almost all research focuses on this part of the math and forgetting why we started this in the first place. It's absolutely unbelievable. The one, I swear to you, this is true, and it happens all the place. The people that, you hear me a lot of criticisms about AI, but this is one thing the AI guys get right. What is all this nonsense here? I mean, there's nothing wrong with doing this. Absolutely nothing wrong with doing this, but you got to come back to this point right here. Right here. Part of this evidence is here is why you chose to do this. Why did you choose this particular mathematical function? That's up here. We're calculating the probability y conditional on that. That doesn't make it wrong or right. It just says conditional on this particular model. But we don't even get this far. We stop here and start talking about these betas and so forth. It's mind-boggling, the stuff that we do. There's good historical reasons for some of this, because getting from here to here, and I'm waving my hands over the math, although we're going to get to the math, which is not simple, couldn't be done by hand. In the old days in the 40s, for instance, when statistics was really taking off as a field, well, it started, even 20 years later than that, but when people really started churning stuff out, everything had to be done by hand. They had those adding machines, the mechanical adding machines and so forth, and calculations were done on these kind of things. So all kind of shortcuts had to develop to get approximate answers. Nothing in the world wrong with that. Nothing in the world wrong with that. Numerical approximation is a fine idea. No problem. As long as we keep in mind that's what we're doing. Our goal was to always say something about the y, and not about these parameters, and not about the math. And the math is just ad hoc anyway, almost always ad hoc. So we need to talk about that, why these ad hoc structures came about, all that kind of a thing, and where did these parameters, why did we get the idea that we could parameterize models like that in the first place? This is going to open up a huge area of research. It turns out that parameters have an origin. Taking finite models in finite discrete time, models like this, where everything is written and absolutely deduced and no problem, no ambiguities, no ad hocness whatsoever, taking into account the measurement characteristics of A, what we know about them or assume, and whatever X we might have, that kind of a thing, and then taking these things to the limit. Now, this has only been done for a few things, just a few models. Most of the time, people are just happy to spit out these ad hoc models, and you can do all kind of math with them. But wouldn't it be nicer if we could always point back to some simple, finite, discrete thing where everything is absolutely known, and that we take a limit and say this is an approximation? Nothing wrong with approximations. We have normal approximations to binomials or something like that. Perfectly fine. Perfectly fine. As long as we keep in mind that's what we've done. We're just using numerical techniques to get answers to questions we can't really get easily other ways. Fine. But so we need to go over all that kind of a stuff. So what a model is going to turn out to be very difficult. And of course, we only talked a little bit about this. All the theoretical stuff, like in physics and chemistry and all these kinds of things, climatology and so forth, what models are. How do we check what theories are, if they're useful, if they're making true statements about the world, or we're just fantasizing? We have to learn how to look at this model in the end by turning it into this form. However we have the theory model, we have to make, if we're talking about the world, we have to make predictions about the world that we can verify. And this is going to turn out, because remember what we did last week, this is going to turn out not to be absolute definitive proof either. Because there's always, remember, for any y that we want, there's any pattern of numbers that we see in the world, there's always going to be an infinite number of models that are going to fit it arbitrarily well. So we have to make assumptions. And in order to do that, we have to use our intuitions, which means we're going to have to go back and use induction intellection, induction rationality, all those things that we did at the very beginning of class. I'm telling you, it all ties together in a quite beautiful way, but in a way that you're not going to see anywhere else. So I've only waved my hands around on this. I haven't done much in the way of proof. We're going to start and build all this stuff up carefully. I'm going to use my book, Uncertainty, and then we're also going to go back and starting on Jaynes. I haven't been doing a lot out of Jaynes because I wanted to get most of the philosophy, but it gets difficult quick. All right, it gets difficult quick. The math gets difficult quick. So this course is going to turn into somewhat more mathematical. But if you rather would just have the explanations of stuff, let me know down below, and I can minimize math or put the math off site or something like this and concentrate just on. I probably won't do a lot of derivations because they're all in textbooks and so forth, and I'm not going to teach you mathematics, but we'll use it. All right, that's it. Thanks very much for listening. Everything is down below, wmbriggs.com, wmbriggs.substack.com. You can read the lesson today. It'll be just this, an excerpt from my book. And next week, we start in with models, real ones. I mean, as they're used, and we'll start building this stuff up bit by bit. Thanks for listening.